We're looking at the last two sections of Chapter 6, Section 6.4 and 6.5. We're going to solve problems that involve the application of exponential equations. Specifically, we're going to look at financial applications. We're going to look at half-life problems and population problems. So recall that we have an exponential function of the form f of x equals a times b to the power of x. The number of x-intercepts is 0. The number of the y-intercept will always be a. So this will always be the y-intercept, which will be our initial value. And b will always tell us if it's an increasing or decreasing function. Remember, if b is greater than 1, then it's an increasing function. If b is between 1 and 0, then it will be a decreasing function. The domain is all x belongs to a set of real numbers, and the range is y, such that y is greater than 0, or y belongs to a set of real numbers. So let's first look at the half-life equation. And in the half-life equation, we have the b being 1/2. It will be a decreasing function, of course, because it becomes half each time. A will be the initial value, the y-intercept. A of t is the final amount. H is what we call the half-life. It's the time it takes for the initial amount to become a half. And t is the time, how much time we're going to consider. What you must remember in all of these problems is that the initial amount and the final amount will have the same units. And it could be milligrams, it could be micrograms, it could be spores, the number of spores or the number of bacteria present. Whereas these two values right here will also have the same unit for time. So when you get confused, you must remember that time is in the exponent, and population, or the amount of mass present, are these two amounts, the initial and the final amount. When we're looking at population, we have A, of course, is the initial value, the y-intercept. Y is also the final amount. So we have y, or f of x, is right here. They are going to be the same units again. B is the rate, so the growth, whether it's decreasing or increasing. And we have to watch out if, for example, something increases, the population increases 5%, then our b will be equal to 1 plus 0.05, which will be 1.05. If, for example, it decreases by 5%, then our b will be 1 subtract 0.05, 5% as a decimal, which is 0.95. And you can see that if it decreases by 5%, then it should be a decreasing function, which is between 0 and 1. C is the time it takes for it to become that percentage, as for H was the half-life, and X is the time that's going to be under consideration. All these formulas we look at will have the same thing. Here we have financial applications. We have A and P, P being the principal, and these will be the same amount in dollars, of course. N is the number of compounding periods, and I is the interest. So we have, some of these are new. Compound interest is the interest earned on both the original amount that was invested and any interest that has accumulated over time. So it doesn't only include what you get now, but you also include the interest. You also get interest over time. A is the future value, is the final amount, is what the amount of the investment will be worth after a period of time. P is the principal, is what the original amount invested or borrowed. I represents the interest rate per compounding period, and that's very important, per compounding period. And N represents the number of compounding periods. So we jump right into an example. The population of trout growing in a lake can be modeled by the functions that are giving us the function this time, where the population represents, or P of t represents the number of trout, and t represents the time in years after the initial count. How long, so this is asking for time, will there be 6,400 trout? Now 6,400 trout, that's the final amount, so we have 6,400 would equal 200, and it must double, the trout must double every 5 years. So we have, to solve this for the exponent, we're going to learn another method in Chapter 7 on how to solve for an exponent in an exponential equation. But right now we go back to our method where we have to get the bases the same. So first thing we must do is isolate the power. We have 6,400 over 200, which equal 2 to the power of t over 5. So we're isolating the power. 8 will equal 2 to the power of t over 5. And we can change, 8 can be a base of 2 because it's 2 to the power 3 equals 2 to the t over 5. And now we can use the common base property. So we have 3 equals t over 5. So 3 times 5 will equal t. So that would be 15 years. A radioactive isotope decays at a rate described by the function a of t equals 600 times 1/2 to the power of x over 1500, where t is the time in years and a is the amount of isotope remaining in grams. Determine the initial mass. So initially, what was the mass of the isotope? And we can tell that from the formula. It will be 600 grams. How long does it take the isotope to reduce to half? So it's looking for its half-life, and that will be 1500 years. The next question says, what is the mass of the isotope after 3,000 years? So it's giving us time and asking us the final amount. So we have a of t would equal 600, it's 1/2 to the 3,000 over 1500. This would give us 600 times 1/2 to the power of 2, which equals 600, 1/4, which equals 150 grams. Now, we can check to see if this makes sense just by drawing a little table. After 0 years, the initial amount is 600. Then, after 1500 years, it does have a half-life, so it's down to 300. And after another 1500 years, it will become half again. So that makes sense, for after 3,000 years, there will be 150 grams left. A deadly bacteria doubles in size every 3 hours. So doubles, here's a key word for us, every 3 hours. There was initially 250 spores. How many will be present after 7 hours? So it's given us time, and it wants to know how many will be present. So we're looking for the final amount. We have a of t is equal to, there's 250 initially, and it doubles, so our base is 2, t over 3. It doubles every 3 hours. And so it wants to know, it's given us time at 7, so it's 250, 2 to the power of 7 over 3. And of course, we know that 7 will be over 3 since both of them are time. This would give us 1,259.92 spores. Now, if we want to check the reasonableness of our answer, we're just going to sketch a little table here. At 0, there's 250 spores. It doubles every 3 hours. So after 3 hours, that would be 500 spores. After 6 hours, that would be 1,000. After 9 hours, that would be 2,000. So if we're looking, 7 is between 6 and 9, so we should get a value between 1,000 and 2,000, which we did. So our answer does seem reasonable. Carbon has a half-life, so we're into the half-life problem, of 5,750 years. It says if a fossil initially contains 36 milligrams and is known to be 8,000 years old, how much carbon will remain if it's 8,000 years old? So we have A of t, and initially there's 36, and it's a half-life, and it has a half-life of 5,750 years. And so we're trying to find the final amount, and it's given us a time of 8,000 years. 36, 1/2, 8,000 over 5750. Don't forget, you must evaluate this part first. If you're doing the equation separately on the calculator, you must do that part first. It's not 36 times 1/2 to the power. We must follow the order of operations. And we get 13.723 milligrams left over. Once again, let's just check the reasonableness of our answer, because we can. At 0, there's 36. After 5750, there will be 18, since it has a half-life. So after 11,500 years, there will be 9. And we know that 8,000 is somewhere in between here, and so we should get an answer in between 18 and 9, which we did. Eastport has a population of 524 people. However, it has been decreasing. It's been decreasing at a rate of 22.5% every 4 years. So here we are with the percentage. We must remember, because it's decreasing, it's going to be 1 subtract 0.225, whatever 22.5% is as a decimal. This will give us 0.775. So we put in our population. I'm going to say P of t is equal to, initially, there's 524 people, and it decreases at a rate of 0.775. That's by 22.5%, which makes sense because this number is between 0 and 1, so it will be decreasing. And we have t over 4. It does this every 4 years. So if we're looking to see how much remains after 10 years, we're going to put 10 in for t. This will give us 277.067, or 277 people after 10 years. If you wish now, you can pause the clip and attempt this one on your own. I'm going to continue with the solution. A half-life of a radioactive isotope is 30 hours. So this would be H, and this is of course 1/2 for the base. How long does a sample? How long does a sample? So how long is asking us time does it take to decay from this to this? So this must be the initial amount, and you're given the final amount. So we have 56 is equal to 1792, which is half-life. We're looking for time over 30. So we're going to solve for time this time. And recall, in order to solve these problems, we have to get the power. We have to isolate the power, get it by itself. So we will have 56 over 1792, which would equal 1/2 to the power of t over 30. We're solving for t. This would give us 1 over 32. It's equal to 1/2 t over 30. Now we can write 1 over 32 and 1/2 as a base of 2. This would be 2 to the negative 5. It's going to equal 2 to the negative 1 out to t over 30. So we have negative 5, which equal negative t over 30. So negative 150, when we multiply both sides of the equation by 30, to equal negative t. So 150 equals t. It would take 150 hours. $3,000 was invested at 6% per year, compounded quarterly. What is the future value after 4 years? So we have a financial application problem here. We have the principal, 1 plus the interest to the power of compounding periods. This formula will be given to us on the formula sheet. It is given to us on the formula sheet. And we see we have our principal amount initially invested was $3,000. Our interest is equal to the 6% divided by 4, because there's 4 compounding periods per year. It's 6% per year, but it's compounded quarterly. This will give us 1.5% per compounding period. So that will give us 0.015. So we have 1 plus 0.015. And the number of compounding periods, n is going to equal, there's 4 compounding periods per year times the 4 years, which equals 16 compounding periods. So you have to be able to determine what it means when it says compounded quarterly, compounded monthly, semi-annually, and all those things. We have 3,000, 1.015 to the power of 16. This would give us 3806.96. So the future value is $3,806.96. Now if I were to ask how much interest was gained, and you can say that, well, the future value, subtract what was initially, that will give you, there's $806.96 gained in interest over the 4 years. So that's another possible question you could get. An automobile originally cost $24,000, and it loses its value by 1/5. 1/5, of course, is 20%. So if it decreases in value, it'll be 1 subtract 0.2 for the rate, which is 0.8. What is the value after 6 years? So we have the value, and I'll go P of t is equal to 24,000 is the initial, 0.8, since it loses its value by 1/5 every year after 6 years. This will give us $6,291.46 after 6 years. Once again, you may want to pause the clip and attempt this one on your own. Joe invests $5,000 in a high-interest savings bond at 9% interest compounded monthly. What will the bond be worth after 1 year? So we have, once again, this formula will be given to you on the formula sheet. We have I is going to be equal to the 9% divided by 12, since there's 12 compounding periods in a year. This would give us 0.75%, which is, as a decimal, 0.0075. The number of compounding periods, there's 12 compounding periods when it's compounded monthly, times 1 year, which will equal 12. So we have, our principal is 5,000. 1 plus 0.0075 to the power of 12. This would give us $5,469.03. Once again, the question could be asked, how much interest did Joe gain on his investment? And that would be $469.03 interest. So in summary, we have a table here, If the compounding period is daily, that means the number of times the interest is paid is 365 times per year. So I is going to equal the annual rate divided by 365. Weekly, there's 52 times per year, and the interest rate per compounding period will be the annual rate divided by 52, and so on. We have the half-life formula, and recall that A of t and the initial value must be the same units, and this must be the same units up here for time. The same thing for here. This must be the same units for time, and the initial amount A and the final amount must be the same. B is going to tell us where it's increasing or decreasing. Here we have financial applications. We have the future value and the principal. Both must be the same unit. We have I, the interest paid, interest rate per compounding period, and N is the number of compounding periods.